Hello, I am Meherchand and welcome in this tutorial on the symbolic mathematics with the Python. The agenda of the present session is how we can solve ordinary differential equation by using SymPy. SymPy is a very specific tool for the scientific computing, one of the important library which can be used in Python. Differential equations play a very important role to study various type of problems in physical science, in engineering, in bioscience, environmental studies, and many more. And sometimes it becomes necessary to find out its numerical solutions because there are various problems which cannot be solved the different type of models which exist by using the differential equations. So in the particular case, we have different type of approaches like numerical methods are there. And recently many intelligent techniques like artificial intelligence is also we are using to solve the different type of differential equations and models. So for all these we need a computing skill, and without understanding the syntax, how we can write the differential equation, how we can operate the different type of operators which are exist in any software. So here we need to apply dsolve function to solve differential equation. So let's start. To solve the differential equation, we are using dsolve function, and first we need to create undefined function by using cls function, and only then we are able to solve the differential equation and to create the differential equation, and then we can apply this dsolve function to solve the differential equation. So we can easily define or create the undefined functions. Fg is equal to symbols function is used at this place. Then quote, we can either use a space or comma at this place, g, then again comma, and cls is equal to function. So this is the syntax to create undefined functions to the symbols. And after defining and creating the undefined function, we can easily write the differential equation by using SymPy. So first we are opening the SymPy live library. Use the URL for the online SymPy is live.sympy.org. So you can see the syntax. sympy.org is the URL for live SymPy, and when you will enter live SymPy, desktop will open online, and if you want to make a full size, you can make its full size. So in the beginning we need to create symbols, which is very quite simple. Of course you can see here symbols already are created in the live mode. So here we need not require it to create symbols, but whenever we are using the SymPy library in the Python, in that case we have to create it. But in the live mode all the symbols are already created here. So here we need not require to create undefined functions. So when you will enter fx, see this is the symbolic function, which is undefined function. Yes, undefined function has been appeared. Now, if we want to differentiate this undefined function, f x then dot df. If is used to differentiate the function, we want to differentiate with respect to x, and when we will enter, so this is d upon dx of fx is the first order derivative of x. If again we enter here dot if, and here we are using x comma x, this will return the second order derivative d2 upon dx square of fx. The same statement we can write in this way: fx dot diff x comma 2, here is 2. So this is also the second order derivative, and by using this statement we can find out, or we can write the derivative of any order. Here I am entering 5. So when I will enter, this is a fifth order derivative of fx. So to represent the differential equation, we can have the syntax. Suppose that we have the differential equation f double dash x, then we have minus 2 f dash x plus fx is equal to sine x. So this is the second order differential equation, and we want to solve by using the symbolic SymPy. So the syntax for the same, we will define the differential equation by using equation. This is the equation. Equation is used for the algebraic equation and for the differential equation. So here the syntax for this one we have is fx dot diff x comma x. Then we have minus 2. The second term is written as product. Then we have the function. Here is fx. Here is fx dot diff. Then we have plus fx and minus is equal to sine x. So we will use here at this place comma sine x. So this is the syntax for the above differential equation, and we are using the same C. So now we are entering here the differential equation. So differential equation will be equal to here equation, then we have fx dot, we have second order derivative. Okay, so we are using here diff, then we have x. Either we can use x 2 times, or we can use in this way also x comma 2. This is the second order derivative. Then we have minus 2 fx. This is 2 product fx. And this is the first order derivative f dash x. We can present here by using diff function. So this will return us f dash x. Okay. Then we have plus fx. We have plus fx, and then comma is equal to, comma is used for the right hand side, and on the right hand side we have sine x. So when you will enter, we have the differential equation is assigned to the function diff equal And when you will enter diff equation and enter, you see that this is the differential equation, which is fx minus 2 d upon dx fx plus d2 upon dx square fx is equal to sin x. So this is the second order differential equation. Now to solve this differential equation, we have to use dsolve function. So we are using here dsolve function, and note the syntax which I am using, how we can define the symbolic variables, undefined functions, then how we can differentiate the undefined function with respect to x, the first order, second order, third order, then how we can insert the differential equation in the syntax of a SymPy. And then after we will use the dsolve function to solve the above differential equation, and the syntax is diff equation. This is the assignment which we use at this place for the differential equation. This is the assignment for the differential equation. Okay, so now we want to solve this equation for fx. Okay, then enter here fx. So when you will enter, this will return us the solution of the above differential equation, and it will take a few seconds. Yes, so this is the solution of the above differential equation, and it is very quite simple to solve the differential equation. Any kind of differential equation we can solve by using dsolve function. Here we are presenting only one example. Okay, and the complete discussion will be when we will start Python, and in the Python we will import the SymPy library and various type of examples for differential equations and partial differential equations with the initial conditions, boundary conditions. We will solve by using this type of operations, and all type of problems are possible with SymPy. At the end, I would like to present one more example. See here, we can directly use dsolve function. This is dsolve, and see that this is the fx is the first order derivative of f. Okay, this is the f dash x. Then we have the product, and we have 1 minus sin x. We have 1 minus sine of fx. Okay, and then we have minus 1. We want to solve this equation for, sorry, this is minus 1. Okay, and we want to solve this equation for. So when you will enter this statement, we have the solution. Sorry, it is okay. We can remove this part. If we have minus 1, then yes. So the solution of this differential equation will appear. Just wait 1 minute. It will return the value. So this is the solution for the equation, which is minus x plus fx plus cosine of fx is equal to c1. Okay, so here you can see that we can easily employ the SymPy for differential equations, and also we can use SymPy for various type of differential equations, partial differential equations, mathematical modeling, and there are various type of numerical methods that also we can do with the help of SymPy, and that's why the SymPy becomes an indispensable tool for scientific computing, and various type of applications are there for SymPy. So thank you very much to see this lecture till the end.